Hey everybody, how are we doing? It is time. We are live. I see a bunch of people in the chat. Good to see you here. Macy, Lauren, Autumn, Maddie, Caitlin, Chase. How is everyone doing? Let's get the chat over here on the side of the screen where it belongs. Abby, good to see you here. What questions are there? What shall we cover? This is your review right here. Doing great, Lauren says. Awesome. Jensen, good to see you. Hey, what's up, Camden, Autumn, everybody? We got the points in the chat. Mubot's giving some points. Mubot, how are you doing?
I am Mubot.
I am not shocked. I am not shocked. We know the test is coming up right here. We got Mubot over here. Can we go over chapter 7? You bet. Well, the Pearson stuff, we do have some videos going over that. And let's do this right now. Let's take a vote. Mubot, you're going to be in charge of this. Let's put in the chapters to cover, and then we're going to take votes. So the chapters, 0 is going to be for pivot. I am Mubot. So let's take a vote right now. You get to control what we do. So technically, if people really want to go over my Pearson stuff, we can. But we're going to vote what chapter to cover. Now, 0 is going to be pivot. So we will vote on this chapter 1, chapter 2, chapter 3, chapter 4, chapter 5, chapter 6, chapter 7, chapter 8. And let's start the vote right now. So remember, it's exclamation mark vote and then the choice you want. And 0 stands for pivot. 0 is pivot. All other chapters are associated. Do not worry that 1 is like a different number. I think they're all right. It's like chapter 1 is chapter 1. Vote for the chapter you want right now. Exclamation mark vote. And then the chapter you want. We'll go in depth on that chapter. Let me go over here to the main screen so we can see this right here. So here's the main screen. Let's zoom in on it. The votes are coming in. Chapter 7's going some wins right now. We got a vote for pivot. Chapter 7's winning right now. Chapter 8's winning. Chapter 5 has some votes. If you don't know what the chapters are, just going over briefly. Pivot is its own thing. Chapter 1 is knowing your variable types. Chapter 2, I believe, is like understanding categorical and quantitative variables. That's what these chapters mainly are, like categorical displays of data, quantitative displays of data. Chapter 4 is comparing distributions. Chapter 5 is the normal model. A lot of votes there. Chapter 6 is correlation. Chapter 7 is regression. And Chapter 8 is regression wisdom. It looks like we have a winner with a lot of votes there. Chapter 7 is the big winner. So let's think about this. You know what I might do? I need to look at some. You know what I'm going to do? While we're talking this over, keep the votes coming in. Brian's going to head over here. He's going to we're making this as test relevant as possible. That's what we like. I'm not going to give away some answers, but never hurts to look and see how things are formulated to come up with some example questions. Who likes example questions? Am I the only person who likes example questions? Anyone else besides Brian like example questions to be like, you could see a question like this on the test. Maybe, I don't know. If people don't like that, we don't have to do that. We could do let's just do completely different stuff. Let's not do example questions. Let's not do example questions. Brian, your example questions, not good. Not good example questions. Okay. I've got stuff up. I'm guessing people like example questions. Do they? They do. The vote is in. Example questions are winners. So chapter 7 has calculation questions. Chapter 7 has multiple choice questions. Chapter 7 has true false questions. Let's think about this real briefly right here. So we do have some jump output to understand. Let's start by talking about some jump output for chapter 7. So chapter 7's the winner. We'll come back to this again. Right now we're going to do chapter 7 and then chapter 5, and we'll come back for a revote here. So let's put a note in here. Starting chapter 7. We're not going to use this. So let's bring up jump. And with jump, let's make our own data for once. I think sometimes it really helps. I'm going to open up a new data sheet in jump. And let's collect some data from everyone in the chat right now. So a little bit of interaction right here. I want you to tell me how many hours you're going to study for the test. We'll be doing that on Monday office hours. Check it out, Robert. We'll be doing it Monday office hours. You bet. So with this right here, need some example questions. You bet. So I want you to tell me how many hours you're going to study for the test and what grade you expect to make. How many hours you're going to study for the test and what grade you expect to make. So let's go here. Put both answers in there. We'll put here study hours. And we'll put here grade. So I want to see both your answers in the chat. You're putting it out there in the world. 1 hour a day. Oh, that's what we said at the start, right? So, and then what would that translate to? So Brian's going to study, for example. Brian is going to study 6 hours for the test, and I think I'm going to make a 93. That's what I'm going to make. So what are you going to study and what are you going to make? See how we have 2 quantitative variables? Exactly, right here, Caroline. Good question right there. We're doing 2 quantitative variables, which is a condition. What condition are we covering right now by saying we have 2 quantitative variables? So we have A's and B's. Give me the numeric amount because we're going to do 6 hours at 80, hopefully. Okay, so we got a 6 and we got an 80. So we got a bunch of 4 and 95. Oh, there we go, 4 and 95. I need to be quicker on my eyes on this. I'm going to bring it over to here to the, oh, well, then you can't see it. 4 and 94. Let me see this. 494, 4, 992. Oh my gosh, I wonder if we're going to get a good association. 578. It's so interesting to see the variation in what people expect. So both of these variables are what now? Both of these variables are what now? Both of these variables that we are analyzing right here are what? Both of these variables are what that we are analyzing. We're doing a regression, so remember this when you're taking the test. We're doing a regression, and both of these are hypothetical people. Both of these, they're going to help with our regression. A statistician is like, you're cheating. You're making data that's going to work for your example, Brian. We'll do some topics right. They're both quantitative. This is QQ, straight enough. We'll see if we have a straight enough relationship right here. This is a small data set. Is it going to be straight enough? Ooh, I don't know. Let's put in another person here who studied 0 hours. And these are expected grades. So we have QQ, 2 quantitative variables. When you hear me say QQ, it means 2 quantitative variables condition. We're going to go here to analyze fit Y by X. We're going to see if we can explain someone's grade. So that's the Y. And we're going to see if study hours explain it. I got ahead of myself because study hours is the explanatory variable. Does everyone notice here as we talk about these variables that when you talk about what is the explanatory variable, you're talking about your X variable. It's the one explaining someone's grade. So does study hours explain why someone gets a certain grade? So the variable of interest, why is it happening? Why do you get certain grades? Is the Y variable. So important we understand what a Y and an X variable is here. Y is the response. And it says factor here, but I like to call it explanatory. It can also be called the predictor variable, and this can be the predicted variable. Lots of different names. I like to call this, let me make it very clear. I like to call this one the explanatory, and I like to call this one the response variable. Those are the names I use. We're good all but one condition here. We're good all but one. If you know which condition we're not good on, you can say it in the chat. There is one issue I see with this. I mean, there's small other issues, but there's one major issue I would say. We could change it. Plot doesn't thicken. If you knew plot doesn't thicken immediately on this one, I'd like this as a test question. I would use this. Probably what I would do, if I made this a test question, I'd probably take this person here and put them to there. And let's go here to redo and redo analysis. If I were to use this as a test question, I think this is a great test question now. So we're really seeing, if you're wondering what plot thickening is, let's go ahead and screenshot this so we can draw on it. Plot thickening is our fourth condition for regression. Let's review the conditions. You ready? And I want you to do the conditions with me. The first condition is QQ. Someone explain in chat right here as we practice, what does QQ mean, or quantitative variables? Explain. We've already done this one a few times right now, but we should know QQ. What does that mean when we say QQ? When we say, does this meet QQ? Is it QQ? What does that mean? 2 quantitative variables, Caroline, you're right. You would say study hours and grade are 2 quantitative variables. So that's required to do regression and correlation. The first 3 right here are for regression and correlation. The next one is straight enough, not straight and up, straight enough. It means, what does it mean? I'm not giving answers. You got to practice it. If you're watching this at home right now, try pausing the videos or try saying it out loud, even if you're just like, QQ, straight enough, no outliers, plot doesn't thicken. What does straight enough mean? What does straight enough mean? So much positivity. Let's throw some 20 points for positivity in chat. Jeremiah, you are right. And the thing is, Abby, great answer right there. A straight line can always go through it, but is a straight line appropriate? Like, does it have a linear fit, we would say? So is a line a good idea? So is the line a good idea? Right there, is it mostly linear? Great answer, Mallory. And so we're just working on our answers, given better and better answers. So what would be an example of something that is not QQ? Something that would be a mosaic plot would be 2 categorical variables. So if you had, this is just like a fake plot inside of here, you wouldn't put inside. But if you had like a yes, no variable, this would be 2 categorical variables. So then you wouldn't meet QQ. So if you have a scatter plot, it is 2 quantitative variables. If you have a mosaic plot, it's 2 categorical variables. So here we see that this relationship is mostly linear. Then we see that there are generally what here? If you notice there are what? What is the third condition? I really don't see things that are really far away. Like I know these are a little further away. This is going to be for the last condition. We're going to talk about this issue right here. But generally speaking, I don't see what right now. And I'll draw an example of what it would look like. I don't see outliers. So, a good plot, like ours looks good. We'll redraw ours right here. It's got a straight relationship, but then ours, this is way more parts than ours has. But you see the scatter gets thicker. If we were to see outliers, then even with our plot the way we have it, we might have saw something, and this is definitely plot thickening, we might have saw something like this. This is where there would be an outlier issue. Does that make sense? The first plot has an issue, and the second plot has an issue, but the second plot also violates the no outliers. So we're not violating the no outliers condition with this right here. So let's draw our bad plot right here, and then what should the plot look like? The plot should have a what thickness throughout. The first one's bad, and then how should the plot look? How should it look throughout? Because we want QQ straight enough, no outliers. And then we want it to look like what? Like this is a perfect regression right here. So first one right here is bad for last condition. Second one right here is good. And so we want it to look what? Like this is the good right here. That's good. And this is bad. And I do also want to mention while people are contemplating this, someone's get afraid chat is paused. What do we want the plots to look like? Oh, there we go. I think someone chatted. Well, we do want it to be linear, but the last condition, QQ straight enough, no outliers, plot doesn't thicken. Exactly. And Peyton, you're right, like a uniform thickness throughout, like the same thickness. That's what uniform means, like same throughout. Because if you have a uniform plot, it's flat across. And this is like the same thickness throughout. Homogeneous, yeah, exactly. It's going to have the same thickness. And we call this homoscedasticity in upper level statistics. Another violation down here would be the following. This plot also has the issue of plot thickening because, because if it gets thicker or thinner anywhere, it's bad. So remember, plot thickening is bad. Exactly. Hannah put it perfectly. Evenly distributed, no fanning in or out. So we also would not want to see, sorry, everybody. We would not want to see something like this. We don't want to change in thickness. We want the same thickness throughout. There we go. We want the same thickness throughout. So all three of those are bad. Only the top one is good. Is everyone clear on the conditions of QQ straight enough? No outliers. Plot doesn't thicken. This is your chance right now to ask about any of the four conditions. With the first three are for correlation, and the last fourth is for regression. Multiple choice, true, false, numeric entry, a lot of things. Good question right there, Walker. Anyone have any conditions about QQ straight enough? No outliers. Plot doesn't thicken. QQ means two quantitative variables, which by virtue of a scatter plot we have. Straight enough means a straight line goes through the data. No outliers means that there's no outliers, and plot doesn't thicken means we don't want the plot to get thicker or thinner. With that, let's look at the regression output and see what we have right here. We're going to make the line, and the line of best fit goes through the data. Someone could argue that there's a little bit of linearity issue right here. So as statisticians, what type of question would this be? Well, we definitely ask questions on conditions, and then we might ask you, let's ask a really good question right here. Are you ready? We could ask you what percent of the variation in grade is explained by study hours? What percent of the variation in grade is explained by study hours? So this would be like a numeric entry question. What percent of the variation in grade? And this is a concept you should know. So I'm going to... If the conditions aren't met, then regression would not be appropriate. That's 68.19% of the variation in grade is explained by study hours. Perfect job. And if you're working on visualization 5, when I say variation in Y explained by X, you know to go to R squared. Great job, everybody. You know R squared is the percent of variation explained. And so, good question right there, Emily. So R squared is known as the percent of variation explained. The definition of R squared is blank percent of the variation in the Y variable is explained by the variation in the X variable. Blank percent of the variation in the Y variable is explained because the X variable is the explaining. If you look at the definitions people are putting on the screen, it's very similar to what we're doing right there. So excellent work, everybody. R squared definition on the screen. Good practice. You could definitely get output like this and need to know where to look, Henry. Great question. You might get output like this. There's questions that have jump output. And so we should understand how to read this output and know that the r squared right here is the percent of variation in y explained by the variation in x. Everybody, great work right now. Let's throw some 20 points to the chat. So with this, let's ask the next question. The next question would be, these are simple questions. Let's do very simple first. What is the slope of the line? 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 Great job. 3.99. And I'm going to delete some decimals here to make this look nicer. Guess that would round. 3.99 is the slope. And we'll annotate that. We'll go to this. Good. I like that. 3.99. It rounds to 4 technically. So that is the slope. What is the intercept? What is the intercept of the line? Which should be pretty obvious right now. And then we're going to review the regression equation right here. You can be like, Brian, you're blocking the screen. Come on, man. Let's take this output. You can see right here, parameter estimates. And chat is doing an awesome job, chat. Great work right there. Now that we have this output on the screen, let's make sense of it. Okay, the regression equation is as follows. The regression equation is y hat. So technically they should have put a hat on this. Hat means predicted, so we're predicting grade is equal to b0 plus b1x. So if you look at this, b1 is the slope, x is the name of the x variable, which was on the x-axis, and then we have here the intercept, which is right here, and then we have here the y variable, grade. Now important, we should note that you do also have, please tell me if I ever make anything wrong, these same estimates down here in this output. Notice how it says estimate of the intercept, like connect this in, intercept estimates. That's the estimate of the intercept. We also have the name of the variable. You can see here the name of the x variable is study hours. So that is the study hours that people were studying. Important to note this. Now let's practice our interpretations right here, and I want you to try typing down in the chat. I'll give you the blank interpretation and then try typing it out. And if you've done visualization 5, you should be pretty good at this. For each 1 unit increase in x, we expect y to increase / decrease by b sub 1. Who has the interpretation here for the slope? This is our practice. So you first need to identify the slope, and then you need to be able to write or understand this interpretation to make sure we know what's going on with the slope. Because one of the parts of your test could be looking at jump output and understanding it. So who has this right here? Let's read some interpretation on the screen. For each 1 unit increase in study hours, we expect the grade to increase by Ben. Amazing job right there, Ben. For each 1 hour increase in study, we expect someone's grade to increase by this amount. Exactly. And does that make sense? Wouldn't that be cool? For each additional hour you study, we expect your grade to increase by 4 points. You might say, well, Brian, that means I got to study for like 2.5 hours to get a letter grade increase. But I mean, if someone told you that you could reliably study for 2.5 hours and get a letter grade increase, you might be like, sure. I'm going to study most of Sunday. I'm going to make, like, instead of making a C, I'm going to make an A. And I'll know that, I mean, it'd be great if you always knew that that return was there. Now, it's expect. We can't say will, so we always need to put this expect word in there. I got to make sure when we do tests in person again and everyone's writing these out, that make sure students do that, because you need to make sure the expect is in there. That's key. How about the intercept? This was slope interpretation. Let's write slope right here. Let's do the intercept. Intercept, which you might say, I'm okay with that. When x is equal to 0, we expect y to equal b0. Who's got the intercept interpretation here? Yeah, you can say on average at the end. I think the expect works for that. Some people are a real stickler on that on average part. I've never been a huge fan of it, but you can say on average, and some people prefer that. So great question right there, Gavin. Thank you for that. And always feel free to tag me, because then it'll like show my name. So for those, and thank you so much if you're here and you don't like you're in another class maybe, but how to tag Brian. I'll show that more. So you can tag me by tagging my name, and then I'll definitely see it. When studies hours equals 0, we expect that. Look at Abby right there, and Adriana and Emily just like boom instantaneously, and Emily and Henry and Ben. Great job right there. This is the practice we need, so we know what the intercept is, we know what the slope is, and we know that these are used to make the regression line. So let's do the following. Let's write a more difficult test question. Let me look at the test questions again right here. Let me see here. Did there? Yeah, I can see it. All right, let me look at them again right here. I'm like coming up with some ideas. Okay, that's easy. I covered that during there's some of these that I covered during the Kahoot. Let's oh man, those are easy. Sorry, you're like, no, Brian, don't say that. Okay, I can cover that on this. Okay. I'm like looking through everything and seeing if I can cover how much. Okay. Ah, it's so easy. I'm kidding. I'm kidding. I'm kidding. I'm kidding. I'm kidding. I'm kidding. I'm gonna go in and write way harder questions tonight. So you're like, man, these questions are a lot harder, and I'll be like, yeah, we wrote way hard. I'm just kidding. I'm kidding. I'm kidding. Okay, I got the questions in my head. They're rolling around in my head. You ready? So, and definitely, yeah. No, the Kahoots has major stuff. Like, remember that the Kahoots lead into the Canvas content quizzes, and the Canvas content quizzes lead into the test. So we got this. I do think there were some harder questions there. I don't want to pretend like everything's easy, but here's what I want you to think. We need confidence. Like, part of acing the test is believing you'll ace it. So I want you to have confidence. I don't want you to think that this is going to be the hardest test in the world. And I think Joshua put it well that the My Pearson questions can be harder than the test questions. So I want you to have confidence, Madison. That's what I want you to think. When I'm saying things are easy, and I think Joshua put it properly, that the test, like someone said that Pearson is harder than the test questions. So does that give you a little more confidence? I would agree with that statement, Joshua. Does that give you a little more confidence right here? And there are practice tests posted, and then the Canvas content quizzes are basically your practice tests. So yeah, hopefully that gives you confidence right here. Doesn't mean don't study, but what is going to be your best example? Huge example. What is going to be your best example of test questions? What is your best example of test questions? What is your absolute best example? No, Kyle, don't feel bad. I had a student make a D on one of these tests, and then they were like, I'm going to fail the class, and they made an A. So don't worry. Canvas content quizzes, Canvas content quizzes, Canvas content quizzes. And there's partial credit for some. There's multiple choice, there's true, false, there's numeric entry. Do not worry if you make a bad grade. I'm telling you flat out, like, I've made very bad grades on stuff that people told me was easy. And I also have the benefit of teaching this for 11 years. So I almost feel bad for saying it's easy, but I want people to have confidence that we have not built the hardest test in the world. And also, I think last semester, we had around an 80 average. So last semester, we had around an 80 average. So if you make an 80, awesome job. If you make above 80, you're above average. And so you got this. You ready? Everyone ready? I need some raise in the chat right here. We need some positivity. We're going to do well on this test. It's not the easiest test. It's not the hardest test. We're going to do right here. We got this, Viren. We got this. We got some raise in the chat. Will each question tell us how many decimals? Yep. And when you review it, tell me if you want, like, if you disagree, and people know I give points back. If for some reason you were graded incorrectly, I give points back. Let's talk about a question or two right here. Just, like, making sure right now. Just saying. When we make this regression line, and we put these things right here, when we have a regression line, so we have a regression line, it goes through the data. Let's zoom in on that. That's way too far out. So we have a regression line right here. Everyone agrees that's a regression line. When we have a regression line, how far we miss by is called a what? Like, this is the actual, and the line right here, we're bringing back Space Pen today for the positivity. So Space Pen is back. The world is a good place. So how far we miss by? Space Pen has all these. So how far we miss by, which it's not really a point, is more just like there's y-hats all across this. Now, people know what we're talking about here. This is a residual. A residual is how much you miss by. So note right here, take a note, that everything on the line is a prediction. We're going to be using this information here in just a moment. Everything on the line, oh my God, that's a crazy Space Pen line. So everything on the line is a prediction, and every point is an actual. Does that make sense that there's predictions and there's actuals? Who's with me with that? that there are predictions and there are actuals. Like the dots themselves are the actual observations. Like somebody actually made this grade right here. Like if we trace over, this is their actual grade. And then if we were to go here, this would be their what grade right here. Like the yellow line, the yellow highlighted portion represents their what grade. So we have the yellow highlighted portion represents the grade that that person who maybe studied for, let's say, 4 hours. They studied for 4 hours. The yellow highlighted portion right here is what they were predicted to make. And maybe this person was predicted to make a, let's say, a 60, but they made a 95. Now, don't overthink it. Don't overthink it. Don't worry about mathematics right now. I just want you to tell me what you think their residual is. So we're going to do a few more examples with this, residuals with actuals and predicteds. 35, Kyle, you're right on track right there. They made their residuals at 35. And Ben, you've got the formula. Ben's showing us the formula right here that residual, which stands for E, is equal to the actual minus the predicted. So I like to say residual wrap. So residual equals actual minus predicted. And the mathematics we're doing right here is that 35, which we've technically solved for right there. Can you go over, for example, like the homework, it was like, calculate the regression line. Oh, yeah, no, that won't do. Good news, Joshua, that won't be on the test. Woohoo! We have examples like that to do practice, but sometimes some of them are just not feasible to make test questions from. So sometimes there's something a little bit harder on the homework than there would be on the test, because we don't really consider ourselves like a hard mathematics course where we want you to do a lot of calculations. You will do calculations. I know, right, Joshua? That's awesome. See, the good news is if you come to these review sessions, I'll tell you, don't focus on that. Don't focus on that question. You don't want to be working that question 3 times. You won't help yourself. Like, yeah, exactly. That's what we do during these review sessions. I'll say, don't do that my Pearson question to practice. We should understand conceptually right here that anytime something has a positive residual, it would be where? Notice how this person, this individual, let's highlight them individually. This individual has a what residual? This individual has a what residual right there? That person right there who made a 95, who studied for 4 hours, they are above the line. So all positive residuals would be what? Where the actual is what to the predicted. All positive residuals would be what? Rainbow Pen battles it out against Space Pen. All positive residuals would be where? All positive residuals is where the actual is higher than the predicted. So just remember, for this test, would you rather have a positive or negative residual? Would you rather score higher than your predicted, which would be a positive residual, or would you rather score, so this person also studied 4 hours, and they made a 25. This person right here, their actual, because this is their Y, they actually made a 25. So when we do you're exactly right, everyone. So when we do their mathematics, we would get negative 35. Unfortunately, we're solving it out at the end right there, is equal to 25 minus 60. And you can see this individual right here with a residual of negative 35. It is because they are negative 35 below the line. Magic color change pen, stop doing it. So they are 35 below the line, and it should be about equal distance. If I can grab that, yes, I can. So you can look right there. They're pretty much as below as the other person is above. So you can see right here, the residual tells us how far the model misses by, and we did a decent job kind of with this sketch drawing of this right here. So a negative residual, which this person is where the predicted is greater than the actual. Can you go over predictions versus actually? Yeah, it's so the line itself, like let's look at our equation on jump and talk more about this example here. I'd like for people to say, so let's do this right now. And I want you to calculate this for yourself. This is the practice we need right here. I want you to calculate for me. Remember what you said your study hours were, and remember what you said your expected grade was. Can you, and let's make our math super easy. We're cheating with this line. This will make our lives really easy. I want you to tell me your expected grade on the test. That's just, we're changing the mathematics. Ignore this now. I want you to tell me your expected grade on the test. What is your predicted grade on the test? Now, this is not a real model. You can't say, Brian, I was predicted to make this. Well, you could tell me your residual then. What is your predicted grade on the test? 80. Well, is it? We'll double check. It could be. Some people are saying 81. Some people are saying 85. And so if you had 81, then you had 4 hours, I'm assuming. And if you said 85, you had 6 hours. Was that, wait, 5 hours, 5 hours. I can't do math. We're just plugging in right here. We're solving the equation, -77. um, and does everyone see what we're doing? We're just plugging in the hours studied, and you would get the values here. So everything on the line is a what value? Everything on the line is a what value? So everything on the line. So yeah, that should be 6 hours, right? Abby, you said you'd stay 6 hours. You're predicted to make an 89. Noel, 81. You'd predict to make, please tell me if I'm doing my math wrong. I'm doing all the math in my head right now as we do this. So it looks like you said 4 hours. Yeah, these are all the predicted. Does that make sense? Every value you're giving me right here is along this line. Now, this person right here who studied 4 hours, now we're using the equation there. This person here who studied 4 hours was predicted to make a what? I want to see in the chat y hat equals this. I want to see y hat equals this for this person right here. Yeah, you use TIs. Anyone can use TIs on the test. We let people use TI calculators on the test. So right here, we see this person who studied 4 hours. Don't worry about the other people. This person alone who studied 4 hours, y hat equals 81. And this is the notation practice we need. So make sure not y though. Y hat equals 81. Make sure to put y hat equals 81 because what are you telling me? And don't look at those individuals. Look at the red line. It might be hard to see. I'm pointing right at the red line. It's trying to make those other individuals appear. But they were predicted to make an 81. So they were predicted right here. Here's their prediction because we take 4 and we trace up and they were predicted to make an 81. And the hat means prediction. Nice job right there, Henry. So the hat means predicted. And then they actually made, let's see what they actually made. They actually made a 95. So tell me about their residual. And I just want you to think about it mathematically. Exactly, Noel. They actually got a 95 and they were predicted to make an 81. So do you see the distance right there? They were predicted to make an 81. They actually got a 95. Their residual was 14. Is this making more sense when you see this? That distance right there, that up and down distance I have means they are 14 above their prediction. So by having a positive residual, they are 14 above their prediction. Now, important note right here, wink, wink, also on the Canvas content quiz, if you were to add up all the residuals, yep, it'll tell you how many decimals, you bet. If you were to add up all the residuals, what would all the residuals add to? Because it looks like some are negative, some are positive. And so these are negative residuals right there. Kyle, good question. And it would equal up to 0. Some are negative, some are positive, and the line of best fit goes through the middle of it. So the closer the dot, the closer the dot is to the line, the predicted and the corresponding dot outside is the actual. So the closer the dot is to the line, the wetter its residual is. The closer the dot is to the line, like this dot right here has a very, very what, but negative what. Like the closer the dot is to the line, like that dot is so close. I think you're saying it, Ben, exactly. It's going to have a lower residual. It's going to have a very small residual because this person right here, what is their residual? That person right there, they made an 80 and they were predicted to make an 81. We just solved, if you're wondering, we have the mathematics down here to solve for a prediction of 4. So what is this person's residual right here who made an 80? Exactly. And what does -1 mean? They are 1 below their prediction. They're 1 below the line. Hopefully, is this making more sense that the closer a point is to line, the smaller the residual? Because think of a residual this way. It's how much the model misses by. So when we think about a residual as how much the model misses by, these are like super close to the model, so they're going to have super small residuals. And you can see that by putting 2 here, you're basically going to get, we might have rounded the equation a bit interestingly because we'll pretend we didn't know. Here for 0, you can see where this individual made a 58 and very easy to tell their residual. This individual right here was predicted to make a 65. So they were predicted to make a 65. And what is their residual? This is probably the last question on this because I think hopefully it's making more sense. This individual right here has a residual of what? And then make sure it makes sense by looking at it because you're going to tell me a number. They made a 58. That person made a 58. What is their residual? So plug 0 in down here. Exactly. And then you want to look at it and you say, okay, we just plug 0 into the equation. Okay, does it make sense that that is 7 below? Does that make sense? Because that's what a residual of -7 means. It means there's 7 below the predicted. Nice job right there, Peyton, showing the mathematics. So remember, all the residuals add up to 0 because that's what the line of best fit does. Now let's do another important concept we should know. What is the correlation here? What is the correlation here? Who knows the correlation on this and can explain how to find it? And then I'm going to do another correlation for practice. Who knows the correlation here and who knows how to find it? Well, there's a linear correlation, correct. And I'm having to solve it in my head. I know what it's about. It's bigger than 0.8. How would you find it? Ben's showing the mathematics. Yep. Exactly, Kirk. Great job there, Kirk. And everybody, thank you so much, everyone, for being here. Let's throw another 20 points to the chat. If you didn't know, we got Mubot.
I am Mubot.
He's there in the background somewhere. And he's giving out points to everybody. Mubot, let's throw out some points and let's give a random quote. I don't know what Mubot's going to say. He's learned a lot over the semesters we've had Mubot. So we have right here, we have the R squared is 68.189% of the variation. Oh, you do mu, of course. That's his favorite quote. Let's go ahead and take this. And there's some important things we should know when we get the correlation. Now, correlation is if you square correlation, you get R squared. If you square root R squared, you get correlation. Pretty easy concept to remember. So if you take R, which is correlation has values from -1 to 1, with -1 being perfect negative correlation. And all the points be on the line. And then you have +1 being perfect positive correlation, and 0 being, there's a few ways no correlation can look. It's going to look like a blob either way. Important to note that something like that still has 0 correlation. Why does this thing I just drew have 0 correlation? Why does this thing have 0 correlation? Q, straight enough, no outliers. Why does that bottom one have a correlation of 0? Why does that bottom one have a correlation of 0? Why does that bottom one have a correlation of 0? If you square R, you get R squared. And this would still be, let's put it right here. R squared only goes from 0 to 100%. So this would still be 100% over here. And we'll kind of talk about what this means right here in a moment. These would be 0%. I'll put above it. Those would be 0%. This would be 100%. R squared only goes from 0% of the variation explained to 100% of the variation explained. And correlation is for linear, exactly R. Q, straight enough. No outliers. Great job, Amelia and Ella and Madison, everybody, Abby. And remember, we got big points coming up with the Kahoot right here. It's not straight enough. So this has a correlation of 0 in the line. Exactly. The shape looks like a 0. Great job, Tori, right there. If you draw around it, you'll get like a 0 shape around it. And then if you draw around these, you get the 1 shape. You get like an up or down 1. The formula sheet's pretty simple on this. It's got the linear equation and it's got residuals. Doesn't hurt. You get scratch paper, calculator, and formula sheet, and writing utensil. Yep. And there's a big thing right here we should note, though. Does anyone notice whenever you're trying to figure out a correlation from R squared, like if you go backwards on this, like you can square root this, but you're going to have to look at something. So get ready for the second example. And we just did one example where we took this and we're going to, multiply. There we go. We're going to take this value right here and we're going to square root all R squared. Thank you so much, Nitin. So good to see you here, Nitin. 474, right, Nitin? So good to see you. Oh, man. Nitin, so good to see you. My hair's getting really long. But Nitin took, was it last summer already? I'm trying to remember, Nitin. 474, right? Working on high. Oh, no, I don't want to say too much. But Nitin, so good to see you. Especially when right. Oh, Nitin, thank you so much for swinging by. I love it. Mubot is all ready to go. Mubot, say hey to Nitin.
I am Mubot.
Puppet Shark, say hey to Nitin. What is going on? Summer. Wow. Yeah, keep up the good work, Nitin. Anytime you want to say hey or have questions, feel free to email me. I love it. Watch this. You ready, though? Let's say video games. Oh, man. I was playing God of War. Let me do something right here. This is going to sort. Okay. Descending. Cool. I was just playing the new God of War. We just beat it. And I just want to say that video game is absolutely amazing. So I am in no way talking ill of video games, but I just want to make a relationship that is going to look, thank you so much, Nitin. God of War, great video game. If you like those kind of video games, if you don't like that kind of video game, maybe play Overcooked, another great video game, or play Celeste. Video games are awesome. With that, here is the relationship between your test grade and how many hours of video games you play. So we want to see if your grade can be explained by your video game hours. Brian does love video games. Ooh, what condition do people see? Playing Mortal Kombat last night. I remember so frustrated with games. That's awesome, Noel. Mortal Kombat's pretty crazy. I played that back in arcades when I was a kid. What issue do we see here? Maybe with this one. What issue do you see with this one? QQ, straighten up. No outliers. Plot doesn't thicken. Overcooked is great, especially if you have someone to play couch co-op with, like 2 people playing or 3, 4, whoever. Or Mario Kart's great, but check out Overcooked if you haven't. You do see, Kyle, you're right. There is a negative correlation, negative linear relationship. Do you see any kind of curvy? Joshua, I agree. That's where I see the issue maybe. I mean, we might be looking at it too much. Then like some Warzone right there. Let's fit the line. You might see the line kind of curves. And you are correct. There is this, I didn't intend for there to be. We're just making up data as we go. But there is a little bit of a non-linear relationship right here. Does everyone see this might have a problem? With QQ straight enough, no outliers. I think Cabal was my favorite in Mortal Kombat 3. He's the one he could throw out like a net and then like swoosh by you. Oh man. And we do have 2 quantitative variables though. So anytime you have a scatter plot, all scatter plots are 2 quantitative variables. Just in case people want, I'm going to show it on the screen right here. This is not a bad screen to take a screenshot of. So take a screenshot of this. This is all the graphics that we've covered. So maybe you're not in our class, you're seeing this for the first time, but this is showing you where you'd have 1 quantitative variable for like histograms, box plots, stem and leaf dot plots. If you have a bar chart, pie chart, Pareto, all these things, you have categorical. I don't like ring charts. A categorical quantitative relationship is logistic, or it's going to be categorical quantitative is going to be side-by-side box plots or stacked histograms. It just depends on which one's the Y and which one's the X variable right here. And I think logistic, that is correct. We don't do logistic in this class. That's a great question, Abby, right there. We don't do logistic in this class. We do it in 320, but we don't do it in this class. And also we should have maybe put with the scatter plot and time plot, you're doing a regression over there. So the regression is quantitative. And those are both bivariate quantitative displays of data. Does this make sense to everybody what you're seeing right here? So anytime you have a scatter plot, you have a bivariate display of quantitative data. So since this is a scatter plot and time plots are scatter plots, they just have time on the x-axis, it is quantitative. But here's the big question. You ready? Ooh, this one's not that bad of an equation to solve either. Here's the big question. What is the correlation on this? What is the correlation on this one? Who knows what the correlation is here? And I'll start solving it. I have not solved it yet. Watch out. I'm going to say no, or someone's going to know the trick to it. What is the correlation? Joshua, you're on the right track. That's not a bad estimate, but let's do better. I think you got it, Emily. Great job, Emily. You got it. And Viren, here's the big catch for it. You ready? Because how do we get correlation from R squared? And so everyone's on the right track. And then some people are seeing it. Exactly, Viren. You added the extra bit right there. And great job, everybody. We know we're all about this positivity. Putting these answers out here, practicing is the way you get it memorized. So if you put a wrong answer here, doesn't matter. Wrong answer on the test, not the end of the world. It's a test. We're going to take R squared and we're going to square root it. And that gives us the correlation. So how did we know this is negative? Like what if I didn't give you this output up here? What if, can I remove the plot? I bet there's a way. Oh, wait, show points. I don't know how to remove the plot. What if we didn't give you this plot up here, which I've never been able to really accurately remove? What if we didn't give you the plot up there, which you can see goes downward? How could you figure out that this is a negative correlation right there? A negative slope, exactly. The slope right here is negative as shown right here and shown right here. The negative slope in the formula, the equation has a negative B1. Great job right there, Addie. It's a very great statistical way of saying it, is that the equation has a negative B1, and we can see this right here, and I know your notation. That's the practice right there that we need. Let me see if there's anything else major I want to talk about. We'll go over here. So let's see. I think that's a really good coverage, and I think like I didn't cover everything, but I think that's a really good. I mean, we just did a 40 or so minute review of regression, and I think that should really help. I think chapter 5 was next, right? Are people feeling better? How do people feel right now? It'll be every chapter pretty evenly throughout. It'll be every chapter evenly throughout. So we'll go to chapter 5 right here next. What or any last questions on regression about anything in this output, about any questions for regression before we end off the regression segment of this? Feeling better? Like that. We will review during class. Yep. And you're welcome to attend both classes, either classes. If you're looking for the link for that one, just let me know. Pivot tables. I think we'll see here. We could revote. Should we do a revote? Revote yes or no? Because I'll do it whichever thing people want. Right now, chapter 5 is winning. Let's do a revote right here just to revote because maybe new people came in. We're going to revote. Cool. We're revoting. 0 is pivot. 0 is pivot. Oh no, well don't worry. I know that's tough. I totally understand actually. Remember, 0 is pivot as you vote. I took some math classes and I've never felt test anxiety until I started doing that. And it was really tough. Like I was shocked at how much anxiety I actually had. I think the best thing to do is to give yourself like practice tests where you sit down and maybe go through the practice tests we have and time yourself, and then work with a time constraint. Because if you do that, the best thing you can do is like make a simulation where you're in the test, and then just kind of the more you get used to it, the better. Because there's definitely the time constraint. I kept looking at the clock when I was taking the math test, so that's the best strategy I think there is. Yeah, and then we could do section 8 looks to be winning out. So 5 is winning out right now. We'll do a revote after 5. So it looks like 5 is winning out. Let me pull up the notes on that. And thank you so much, everyone, for being here. So let's go to 5 and start talking about some chapter 5 right here. Let's start talking about some chapter 5. I like these questions. Oh, man, I like these questions. Okay. So there's important things. I'm looking over everything right here. Right, yeah. Let me see this one. 2 seconds. Yes. Okay, good. Okay. We'll review this to start. Okay. I've got in my brain what we're going to do. I've got a whole list of things. Let's stop the vote. The vote has been stopped. And the winner is chapter 5. And let's start talking a little bit about chapter 5. Chapter 5 is all about the normal model. Chapter 5 is all about the normal model. So let's put here chapter 5, normal model. Okay, so we have some big topics to talk about in chapter 5. And some of the big topics include, when do we use the normal model? I know this is just totally, when do we use the normal model? We're going to start with like, when would we even use the normal model? Like, when would we even use the normal model? Don't worry, it's like not this complex answer. It's not very complex. You'll be like, well, of course. When would we use the normal model? You're basically right, Peyton. And so when there is a normal curve, when the data is normal, Ben, that's exactly it. Parker, you're right. We use the normal model when the data is normal. Would there be a normal model drawing to reference law test? There won't be, but you can draw one out on your scratch paper after. You can't bring notes to the test, but you can start the test, show your blank scratch paper. You can draw a thing, you can do work and get your work on the paper while you're doing it. You can't bring notes. You do have scratch paper, but you can draw one out. So let's put a big note right here. We need to know, or we need to have good evidence the data is normal. So interestingly enough, we do this a ton in 320. What if your roommate is also in 201, has the test same day? Can you take it in the same room so you don't talk to her? Yeah, I mean, I think that works, Madison. Just, we really try to not make false positive accusations. If people are taking it and it's pretty clear that they're not, like, you just don't want there to be any, like, during the exam, your friend's like, hey, how you doing on the exam? You don't want to do that. You can have the printed formula sheet. That is correct. And it is on the Stat 1 webpage under the exam section. So how do we know the data is normal? And so I really like this right here. Let's take a look at this. Take a look at this. You ready? You're like, Brian, no, we're not doing this. Take a look at this, right? Really? You can have that error already. Don't save. I'm going to show you something right here. Don't be sus. Don't be sus. That's the key. You can do that, but just don't be sus. Please don't be sus. So let's go right here. Let's run this again. Oh, I know why. Brian is a fool. Now Brian's not a fool. Okay, here we go. This is something you've seen before. This is called a what? Now, a lot of people have forgotten this. This is also in jump, so I'll show it over here in jump too. So I can show this in jump. I just like making it in R better. So I'm going to make one in jump while we do this. Here's the way to do it in jump. What is this thing called that a lot of people forget about? People are like, I've never seen that, Brian. You're making things up. I swear I've never seen that. I'll go to the notes. I'll show you. Oh, look, there it is. Giving me tangent vibes. So this right here is called a what? And jump calls it more by the name we know it by if we look right here, right there. So this is called a normal, and let's remember the way to do it right here. So all of a sudden someone's going to have an epiphany, I hope. We call it this. We call it a normal probability plot. And so what did I ask you to do when we first encountered this? If you're in my section, what did I ask you to do when we first saw a normal probability plot? When we first saw a normal probability plot, I asked you a certain way to read it. Whenever we saw a normal probability plot. I wanted you to read it a certain way. I think I did it for both sections, I'm pretty sure. Well, how did I say to read normal probability plot? How did I say we should read it? I'll give it a few more seconds here. Like, wait, how are we supposed to read it? There's a way we're supposed to read it. Backwards, Emily, great job. Plot probability of normal. That's what it does. It plots the probability of something being normal. Great job, Emily. Emily, we're throwing 50 points for Emily's answer right there. I'm so glad that people remember that. But we read it backwards, 50 points to the chat right there. So it's a plot that shows the probability of something being normal. Read it backwards to hopefully help it make more sense. And there's two versions of it that we see. The two versions of it that we see are going to be one that looks normal and one that does not look normal. If it looks normal, you will see right here on the normal probability plot. So it's going to have these bands either way, and it's going to have a line going through the middle. So when it looks normal, you're going to see right here the dots are going to follow the line mostly. So if it makes this linear pattern, this is when it is good. But the other version is one that does not follow the line. So in this version right here, the line is not followed. And this is the one where it's not really normal at all. Does that make sense right here? That a normal probability plot shows us the probability something is normal. So why does this matter? Why does this matter? And I'll show you why I like showing this in R right here. Because I'm going to make some data right here. I'm going to make two versions of data. The first version of data is going to be normally distributed 1,000 points. So tell me, how does a normal distribution look? How does a normal distribution look? A normal distribution looks how? A normal distribution looks how? How does a normal distribution look? We should know the words for normal distribution. A normal distribution, does it matter what type of... Nope, you can use, as long as it doesn't have internet capabilities, you're good. A normal distribution looks unimodal and symmetric. Great job right there, Ben. You can see the unimodal symmetric distribution. So that means the QQ plot, let's look at our notes. The QQ plot should look how? So this is one, so let's put right here in our notes. That means the QQ plot, so start typing in the chat, how should, since we have a normal looking histogram here, looks pretty normal. How should the QQ plot look for it? How should the QQ plot look? It should follow the line exactly. So this is just me showing it with data over here. So there's the histogram, and then there's the QQ plot. Follows the line pretty well. Nice job. Good to see you here, Andrew. So now we see this data looks how? Let's look at our notes. This data looks very what? Just describe the histogram right here. How does this histogram look, which we see on the screen? So that histogram looks how? How does that histogram look? Looks very right skewed, right to the high, left to the low. And see, we can review some other concepts here. Right to the high, left to the low, whatever way the tail goes. And this goes towards the high numbers. So this is right skewed. Good practice, everybody. So what does that mean the normal probability plot will look like? Of course, statisticians have to have multiple names for this. The normal probability plot will not look normal. And I should have done, yeah, this is left skew. So technically it just doesn't follow the line. So we can try to make ours look like that because of course I did a left skew to this. You don't need to note that in depth. No, we lost something there. So if it generally, how did it look? Push to the left. There it goes. Oh no. As long as it doesn't follow the line, it is not normal. And so this would not be normal. And the one we see on the screen right here is also not normal. So do you see how it's not following this line right here? It goes away from it. The ones that are normal are going to follow the line, and that's from normal data. And so this is the good one. Normal data looks like this, and not normal data like this will not follow the line. Not normal data does not follow the line. And it wouldn't matter so much if it looked the other way where it looks like this. So here's a histogram that's skewed left, and here's a left skew one. So once again, this is not normal. Now we have one other way of testing this. So let's look at the other way of testing to see if something is normal. It's going to see how what the normal curve fits on the distribution. So we're going to look at this right here, and we're going to see how what it fits. So we're going to see how, like, not bad, but we're going to see how what it fits. So this bottom thing we're going to do right here is going to be called a what of fit test. We're going to put a normal curve on top of this. You see I drew a red normal curve for the other one. This is called a what test down below here. Goodness of fit. Great job right there. So these are normal, well, those are normal probability plots. These are histograms. It's a goodness of fit. And so when you think about goodness of fit, what does it mean to have a goodness of fit? A goodness of fit is telling you just how good that distribution fits on top of it. So the null for this, we don't talk about nulls that much for this test. The null is that it is a good fit, and the alternative is bad fit. So let's put right here null, good, and alternative bad. So the null is your starting belief. You currently believe that the fit is good, and you are going to see if there's evidence it is bad. The null is that it is good, and the alternative is that it is bad. What's the difference between the goodness of fit and line of best fit? So the goodness of fit, think about this. So the line of best fit puts a what through the data. So this is a goodness of fit to see how good the normal curve fits, and the line of best fit is going to fit a line through the data. So this is the line of best fit, and then a goodness of fit is going to see how well this histogram right here fits on the data. And what would you say about this one over here? That this one on the right is a good or bad fit for this data. Do you think this normal curve is good or bad on this data? What do people think right here? What do you think? Is this a good or bad fit on the right? Like, is this normal model fitting well on the data when I try to put it? It's a bad fit. How about this one over here on the left? Is this a good or a bad fit? When we think about the goodness of fit for plotting a normal curve on top, is this generally a good fit or a bad fit? This one's a good fit. Great job. Good practice right there. So when we look at the goodness of fit test, it's going to give us a p-value. And the p-value is going to tell us whether or not we reject the null or we do not reject null. And here's some great practice. Great job, Autumn, Jeremiah, and Jensen, Tori, Kirsten, everybody in the chat. When we do this right here, we're going to get a p-value. And we have a famous saying in this class: when the p-value is low, reject the null. When the p-value is high, just let it fly. When the p-value is low, reject the null. When the p-value is high, just let it fly. So I want to see that in the chat. When the p-value is low, reject the null. When the p-value is high, just let it fly. And that just means just let it be. Don't reject it. So start putting in the chat. This is practice right here. When the p-value is low, reject the null. When the p-value is high, just let it fly. So let it fly means don't reject, or fail to reject, some statisticians say. Statisticians watching this in the background. If the p-value is low, reject the null. If the p-value is high, just let it fly. Just let it be. Don't reject that null. When the p-value is low, we need more people in the chat practicing right here. When the p-value is low, reject the null. When the p-value is high, just let it fly. If the p-value is low, reject the null. If the p-value is high, just let it fly. Great job right there, chat. Got some people practicing in the chat. Let's throw some 20 points to the chat. So what does this mean? Like, we memorize things, but then we have to know what it means. Well, when we do our test, we are either going to reject the null or fail to reject the null. That's an old way of saying not reject. I mean, think about a dichotomy right here. You either reject the null or you do not reject the null. Like, you have to do one of those two choices. It's either this or not this. You either reject the null or not reject the null. So I like to say not reject. So when we do this right here, I want you to think about what this p-value means. I just want you to kind of like talk about it without using stat words. This p-value right here, is it high or is it low? Let's put this down as the p-value. And we'll put a note down here on the bottom for anyone wondering. Low p-value is less than 0.05. A low p-value is less than 0.05. That p-value is high because a low p-value is less than 0.05. That's what we consider small, statistically significant, i.e. unlikely by random chance. So I just want you to think, are you rejecting the null or not rejecting the null right now? That's all I want you to think about. For this first one right here, for this one, are you rejecting the null or not rejecting the null? Remember, you're saying when the p-value is low, reject the null. When the p-value is high, just let it fly. Great job right there, Abby and Michael. So what does that mean you would believe about this? Now, you're not saying this is true, but what would you say to somebody? I would still believe what? Because you started off with this assumption, and then you would say, exactly, Henry, that's what we're getting into right here, because you're going to not reject it right here. Since you're not rejecting the null, you would say, I still believe. And so this does, Ben, hopefully I can kind of converge that into it, because we'll be talking about the next one, which will be. So what would you say, like, just explain it in words. I would still believe that it is normal. Does that make sense to say for that first distribution, which we're looking at right here, I do not reject the null, that the normal curve is a good fit. I still believe it's normal. Now, how about this second one? Who has some guesses for the p-values? And I think this is where there might be some aha moments. Who has some guesses for the second one, what the p-value for it might be? Who has some guesses for the second one for what the p-value of it might be? What might the p-value for the second one be? The p-value for the second one might be very what? The p-value for the second one is going to be low. Exactly, something less than 0.05, very low. Now that means you're going to do what here? Since the p-value is low, you're going to reject the null. So you're saying now, I have what? I have evidence that the normal curve is a bad fit. Different assumptions. So we have evidence here that our results would be unlikely to occur by random chance, given that the normal curve is the correct fit for the data, Kyle. That's a real technical way of saying it when it comes to p-value. But when we think about this test only, at least understanding this right here, evidence that this distribution will be unlikely by random chance, given that the data came from the normal. Because the null is that the data comes from the normal, which means the normal curve is a good fit. The alternative is that the data does not come from the normal, which means the normal curve is a bad fit. So when you reject, okay, this is a tough concept. That's why we're going a little bit slower here, and I love all the questions. So the easiest thing to see right here, at least if you're just like, I need to put this in my head, which we try to go for all different levels of knowledge on this, is that when the p-value is low on the goodness of fit test. Oh, that was just a guess right there, Sam. Great question, Sam. We're just kind of making it up. It would be very low. And so when the p-value is low on the goodness of fit test, it would mean you have evidence that the data is what? When the p-value is low, no, it wouldn't, Janie. Great question, Janie. It would, even if we had a mirror image, great question right there. Yep. So it'd be, yep. And when the p-value is low on the goodness of fit test, that would mean you have evidence what? So when the p-value is low on the goodness of fit test, that would mean you have evidence that the data is what? When the p-value is low on the goodness of fit test, that would mean you have evidence what? Kind of like a very technical, I want to see. So when the p-value is not normal. That's what the goodness of fit test is doing. We're all talking about just checking normality right here. So when the p-value is low on the goodness of fit test, we'd have evidence that it's not from a normal curve. When the p-value is high on the goodness of fit test, you would what? Still believe, because you're not going to reject the null. Does that make sense? And low p-values are statistically significant. I have an option right now. Would you like me, option 1, to go in more talk about p-values and how they're used throughout the test, or option 2, do examples with the empirical rule? Which one would you like? Statistically significant is anything below 0.05. So this p-value right here is statistically significant because it's below 0.05. Would you like a more in-depth talk on p-values, or would you like me to go to empirical rule? Looks like empirical rule examples is winning. So empirical rule example, I'll do empirical rule example. I figured it'd be empirical rule example, both. We can loop back here, Janie, afterwards. So someone could just type 2222 in the chat like repeatedly. Okay, we'll come back. We'll try to do p-values in a little bit. Remember, we are doing a Kahoot in a little bit, so $50 grand prize. Woohoo! Okay, let's do some empirical rule examples. Okay, let me look at those questions again. Empirical rule is winning out. Okay. Okay, yeah, that's easy. I got that. Okay, here we go. Okay, what are we gonna collect data on? I want you guys to think of the question because I come up with two. I go to Taco Bell for every question. Man, I miss Taco Bell. They know they're messing with me, those nacho fries. The amount of nacho fries sold at Taco Bell is normally distributed, key assumption, each day with a mean of 200 sales and a standard deviation of 30 sales. Use the empirical rule to solve the questions below. You know, this is horrible to say, and I don't want this to ever happen. If Taco Bell gave me a lifetime supply of nacho fries, that would be like the best day and the worst day of my life. My life would just be over. Like, I'm already trying to work on my diet and my exercise. That would just ruin me, but I'd be like so happy. I'd just have like a bucket of nacho fries and a bucket of nacho dip. Like, so good. They're so good. Man, are they different right now? Did they change the nacho fries? That'd be like, I don't want that. I don't want that, everyone. They better not mess with my nacho fries. If they do, nah, I'm out of here, man. They better not mess with my nacho fries. They better not do that. Okay. So let's use the empirical right here. Do you know that nachos are just tacos? What? Andrew, you're awesome. That sounds like a Mitch Hedberg joke. Oh, Mitch Hedberg, miss him. What percent of days would you expect them to sell more than 260 nacho fries? What percent of days would you expect them to sell between 170 and 260 nacho fries? How many nacho fries? I just want to write nacho fries all the time. Rib my Chipotle chicken. Oh no, did that go away? Gosh. How many nacho fries would they sell on the worst? Sure, let's go easy. 2.5% of days. And last but not least, what is the 84th percentile of nacho fries sold? Okay, we got lots of different questions, all dealing with nacho fries right here. So the first thing they do, oh man, so now we need to start like a petition right here. Bring back the Chipotle chicken griller. Make it happen. So what's the first thing you would do on your scratch sheet of paper given this? Here's the Brian's like pro tip. I need like a pro tip with Brian thing. I need the screen to be like pro tip with Brian. I'll make it happen. So what do we need to do to solve this question right now? Scratch sheet of paper is going to be a huge thing. I got chat. Draw the normal curve, Henry. Great job right there, Henry. Henry, excellent advice. I brought us off topic by talking about nacho fries. It's my fault. Let's draw the normal curve right here. Okay, the first thing I usually put underneath my normal curve is what is the first thing? Oh, great normal curve now. What is the first thing I put underneath my normal curve? First thing I put underneath the normal curve is the what's. So everyone start giving Brian hints as he draws his normal curve. What's the first thing I usually draw underneath my normal curve right here? The first thing I'm going to usually draw, the mean. And so you are correct, and so 3 standard deviations. Nice job right there, Parker. These are my 3 standard deviations. You are correct. Each one of these is a standard deviation up, and the mean is at the center of the curve. So, and I might start putting the empirical rule. You're correct. I'll do the empirical rule, but I'm always going to put this at the bottom. I'm always going to put my z-scores. So I'm always going to do this right here because this is kind of for every single curve. We could just use this right here. Like there's the z-scores right there. Just the standard deviations up. Like this is 1 standard deviation up, 2 standard deviations up, 3 standard deviations up right there. Oh yeah, and Kyle knows the 0.15, 2.35, 13.5, 34, 34, 13.5, 2.35, 1.5. Oh, Kaylin, thank you so much. Glad to have you here. And feel free to check out, this is recorded, so you can check it out later. So now we're going to take these numbers and let's mark our question. In this question, we need to know that this is the what. So the thing in the yellow is the what. Help me out with the thing in the yellow. I'll solve the other one. So that's going to be the thing in the blue right there. That's mu. Oh my gosh. Help me out with the other one. That's the mean. Exactly. That's the mean. Brian, do you even know stats? I learned stats last week. So that's the standard deviation right there. And the question does say that it's normally distributed, which is an important thing we should note. And this leads to the notation with the green pen. Leads to the notation right here where we could say that something is normally distributed with a mean and a standard deviation. So we could plug in these numbers right here. That's what that big N stands for right there. And then we have here the 200 is the mean, and the standard deviation is going to be the spot right here. Very important we know this sort of like way of talking about it, that things are normally distributed with a mean of 200 and a standard deviation of 30. And let's go back to our drawing and let's put in the numbers. So with this drawing right here, we can go ahead, put our context numbers in, and we put in 200 right here, 230, 260. Why am I drawing these numbers? A lot of people get confused, but I want to know why. What am I doing each time I go up, down, or up a standard deviation? What am I doing? Now you can double check your work in your calculator. Please tell me if I get something wrong. But what am I doing right here? Great job, Ella. Good practice. What is Brian doing right here every time he does this? Exactly. Great job right there, Jensen. I'm just going up and down a z-score, and every time I do this, it's 30, and I'm just adding that to 200. So I'm just going up and down a z-score. I'm just going up and down z-scores, which are going to be how many standard deviations we're going up and down. So the first question asked, we could do like a small version of this. The first question asked, or let's grab the question and put it below here or above here. That'd be good. The first question asked, what percent of days are you expected to sell more than 260 nacho fries? So what do you instantaneously notice about 260, which is something you would notice for any sort of empirical rule question? Like the question is going to say then, like, use the empirical rule to solve. I think we said that earlier, but all these questions are empirical rule questions. What do you instantaneously notice when you draw this out? What do you instantaneously notice? You're close. Kyle, you got it right there. Great job, Kyle. And so we can start drawing some stuff. Everyone's got the answer. And the first thing you might notice is that it's 2 standard deviations above, exactly. And then Jensen gives really good advice right here that we should know 95 is within positive or negative 2. Great job, Jensen. 95% within positive or negative 2. And we'll probably keep this for our problem right here. What I'm drawing in black is things that can stay no matter what problem we're doing. That's 99.7%. I'm going to try to draw it a little bit better as best I can. You know what I can do? I can zoom in so we actually make it look decent. As best Brian can write. Look at that. If you try hard, your dreams will come true. You'll write legibly. That's my dream. And so last but not least, we have this one right here, but we're not using all of these numbers right now. We're just using a few of them. 68, 95, 99.7, just to make that bottom one the middle one look a little clearer. That is 95%. That is 95. The numbers on the screen are 68, 95, 99.7. And what I would do then is I would drop down a line to where we're talking about, which is right here. And then what do you notice? What do you notice? And the green things are things we're going to erase afterwards. What do you instantaneously notice about this? That there is what percent inside of this? There is what percent inside? And I think I made it look a little odd. I'm going to draw it a little better because I could see how someone might get confused. There we go. That makes it look a little better. What percent is inside of this? What percent is inside of this? Thank you so much. I think someone, oh, you was talking. What percent is inside of this? Because we're interested in just this right now. 95% inside, 5% outside. So the total outside is 5%. The total outside is 5%. So what does that put on either side? It puts 2.5%. So there's 2 is this making more sense? So the answer to the first question right here is 2.5%. The answer to the first question is 2.5%. Who's with me on this one? Like, got it, Brian. Easy question. I understand that empirical rule 1 right here. So we've solved this one. Now let's look at the next one. I think everyone's good on this one. Let's do the next one. Back in time. Gotta get back in time. This one's more difficult. This one is more difficult. And so this uses the empirical rule 2. So let's add some notes up here at the top. What do people notice about this right here And what do people notice about this right here? So start helping out with some notes right here. What do you notice? Because the question's not probably not going to tell you these things. What do you notice about Z, or what the Z-score is for 170, which will tell you what a Z-score is, because I think you got it right there. That, wait a minute. Yeah, that is correct, I think, Ella. Ella, great job. That is the answer, I think. Within one standard deviation of the mean. Exactly, and it's a Z-score of -1. So this has a Z-score of -1, and we can see that down here. And then this has a Z-score of 2. So turning these things into Z-scores is probably going to help us some with understanding where the answer is going to be at for this. So now let's go ahead. I'll go off the screen right here. Let's go ahead and plot this. Great job right there, Emily. Excellent practice. The more you're practicing this, I do notice people with higher points do higher on the test. Now this one seems, there's so many ways to solve this one. This one's more complicated. I'm going to break this up into 2 regions right here. Let's go ahead and make region 1 and region 2. You ready? So I want for you to tell me the area for region 1. And then I want you to tell me the area for region 2. I think this is a good way to solve this one. There's many, many ways to solve it, and hopefully I'm doing a pretty kind of easier solve for it. The yellow region has how much area in it? We're going to talk about the yellow region first. Let me click on it to show we're talking about it once I get this one shaded in pretty well. The yellow region has how much area in it? I think chat's probably going crazy with that answer. You got it, 34. Can anyone explain how you got 34 right here? How did you get 34 right here? You might be able to do some cool stuff. Oh, we can. Watch this. Let's do, oh no, that's not what I want to do. Oh, that's so lame. Look at it. Because over here, if I had done it perfectly, it would be just half of 28, or half of 68. So this right here, it's half of 68. So this right here we know is 34. Let's go ahead and put 34 right here. We want the total area, not just one of these. So that's 34%. Now, how are we going to get, and if you notice I did a trick right here, how are we going to get this area right here? So this area right here, how are you going to get that area? How are you going to get that area right here? And there's, ooh, we did really well on that one. So how are you going to get that area right there? This area, how are you going to get this area right here that I'm highlighting right there? That one that's blinking for you right now. You got it. And does everyone see what I did? I literally showed that if you were to flip it, you would get the other portion, the 95, because between here and here is 95. So as best I can draw, this is half of the 95 area. So that makes this 47.5. Everyone's showing it mathematically on the screen right now. Divide 95 by 2, and this is 47.5. So what's the mathematics for the answer? What is the mathematics for the answer? And I'm just throwing another 20 points. Great job. So many people answering questions. That's what we like to see right here. What is the mathematics on the answers? Exactly, Cody, you're right. And Ben, you are right. That is the answer. You're just adding up the 2 values right there. It is 81.5. And great job. I think Ella got it like instantaneously, ready to answer these questions. Great job. So, yep, 34 plus 47.5. And that will give you 81.5. So excellent work. Who thought this problem was pretty hard to begin with? Was anyone like, ooh, this one's going to be tricky? Like, did anyone think this was a more difficult problem? And then we just totally aced it, which I hope people are like, I get it now. That one's not that bad. So hopefully it makes more sense right there. Oh, you did it that way? Yeah, that might work right there. Does that work? Yeah, I think you did it correctly. Great job right there. Let me just show what, who said that? That was a really great answer. Henry, great answer. Henry solved it differently though. So I'm gonna show Henry's solve on that one real quick. Yes, here's Henry's solve. And I do think it's a good way. Henry took the following. He took the 68 to begin with. Great solve right there, Henry. Henry took the 68, which is here. And so he said that's 68. And then he took this right here by taking half of the remainder because he had 2 areas. Now, he didn't want this area right here. So he took half of the remaining kind of area. He found this area right here, this area plus this area. He found that by going 95 minus 68. But then Henry only wanted what of this? Henry only wanted what of this? Exactly. We used to be relying on David M. Lane, but now we're good. So that's 27% because we subtracted the 2 areas, and now Henry only wanted half of that. And so then he just added that to 68. And that's how Henry solved for this. Oh, no. So amazing work, Henry. You just earned everyone another 20 points right there. That's a great way to solve it too. And I hopefully by drawing these out and seeing it, oh no, we didn't do it. Points. I hope seeing the kind of shading helps. This is how I see it in my head. I see a lot of things. Jokes. So how many nacho fries did you sell on the worst 2.5% of days? I bet someone knows this pretty instantaneously. I bet someone's like, who knows this one really instantaneously? This one right here using the empirical, and it will say something like, use the empirical. You are correct, Ben. You are correct. 140. And don't worry, like I see a lot of people make the mistake right here. It's a very common mistake to say 110. Don't worry if you said 110. This is the practice because I did this one on purpose because a lot of times people say 110. They usually go to the third standard deviation. The third standard deviation, how much area would be below this? If 99.7 is between here, what's total outside of this? Like we're going off the screen right here. What is total outside? Outside point exactly. So this is the top 0.15%, and this is the bottom 0.15%. And then down here is the bottom 2.5% and the top 2.5%. And this is very similar to the first question we did. That's a 1. That's horribly written. Is this making sense right here that how did we solve that there is 2.5 on either side here? How did we get these 2.5s? This is the practice we have to have right here. How do we get that these 2.5s are on either side? Because if we go across all of these arrows, what should we get? It's a good check to make sure when you draw these arrows right here, that if you go across all the arrows, you should get what percent? Exactly. Hey, what's up, Adam? So good to see you here. Thank you for swinging by. I love it. Exactly. So we're taking the inside 95, saying outside is 5%. Exactly. And then you are correct, Ben. Yep. 13.5. I think, do I have that graphic up? Let me pull that up. For those wondering, because sometimes, and I'm more than honored to have people here who are not in our class. Like some people are like, Brian, can I watch your stream? I'm like, yeah, anytime we're live on YouTube, join in. Join in, have fun, answer questions, get some points. I don't know. If your instructor is willing to value the points, then they're worth something for your class. We're going to pull up the normal curve model right here. If you don't have a screenshot of this, feel free to take a screenshot. So this right here, sideways screenshot, there we go. And so here is the normal curve model. Let me go full screen on it. And there is all the numbers on it. So finishing report, awesome. And so I think it was it Ben saying 13.5? There's the 13.5 Ben right there. If you can see it, it says 13.5, 0.15, 2.35, 13.5, 34, 34, and it's symmetric across. Oh, thank you, Jensen, so much. Yeah, we're here. Terry's awesome. I'm honored that Terry's working on 320 with us now. He's part of the 320 team, and he's great. Like Terry's got so much positive energy, and Terry's a great teacher. So we're just here to help out, and you know, I really just like the whole YouTube thing. I mean, I like YouTube, and you know, the stream's been going well today. We haven't had any lag. Sudden Link, thank you, Sudden Link. Puppet Shark, are you thankful of Sudden Link being good? How did I know you're gonna say that?
Tiny Brian, how about Tiny Puppet Shark? Thank you, Tiny Puppet Shark.
Okay. Practice, practice, practice. That's what we need. Practice, practice, practice. Okay. Let's do this last question right here. The answer to this one was 140. If you didn't catch it, the answer to this was 140 before we started just Brian losing his mind. The answer was 140. So let's look at the last question right here. The last question is, I think it was like the 84th percentile. So if you notice, I'm kind of going back and forth asking different type questions right here, covering different concepts. Now, when we talk about percentiles, do you want to be in the 99th percentile of the test or the first percentile of the test? You're like, yeah, I'm the first percentile of the test. Which would you like, the 99th percentile or first? Calzone, so good to see you here, and you better compete. You better be here, Calzone. Fan favorite, Calzone Tyrone. Man, we got all the favorites coming by today. I love it. Everyone wants 99th percentile on the test. So when we think about the 84th percentile, Calzone Tyrone showed up to our first Kahoot we did on YouTube. And I think, what'd you get, third place or second? And there's prizes. So the 84th percentile. So when you think about percentiles, it works the following way. Percentiles go from left to right, going like first, second, third, fourth, fifth, 10th, 11th, 12th, 20th, 30th, 40th. What are we at right now? What percentile has Brian shaded up to on the curve? And you are correct, Ella. Great job. Second. Yeah, that was awesome. I was honored that. The 50th. And wait a minute. So wait, if we're at the 50th and then we do this, well, how much is that blue area worth? Because we're at the 50th. The 50th percentile is right here. And then how much is that blue area worth? And mathematically show it. Great job, Emily, right there. You are correct that this is worth 34. And so wait a minute. All of a sudden now it looks a lot to me like maybe this spot right here is the 84th percentile. Now that's 34% of the curve. It's not the 34th percentile. Half of 68 exactly. Is this, hopefully is giving more confidence here to understand where these, so 230 nacho fries, we're always talking about some nacho fries. It might be my dream for us to be sponsored by Taco Bell. I mean, I shouldn't talk about my dreams, but you know, Taco Bell's awesome. Someone's like, Taco Bell's horrible. I'm like, I disagree. Respectfully disagree. I will debate you on that, on how awesome Taco Bell is. What questions do we have right now? Let's open the floor for ideas. I think we've done a good review of empirical rule. We've done regression so far today. We've done, and I'll take the votes. We've got about another 25 minutes or so. I'm going to take like a 10-minute break before we start streaming again. I'll probably end right around 6:50. So we'll do another topic right here. The answer is 2:30. Correct. The answer is 2:30. Boom. Answer right there. Put your topics in the chat that you want us to review. I think there's been, oh man, Cody, thank you so much. Cody, let's throw some 20 points right there for some Taco Bell positivity. What's going on? Taco Bell for dinner. Oh man. The second question, I'll try to do a quick review of it while people say what they want us to cover. This is your chance right now to say, hey, Brian, can you cover this topic? The second one was, what percent of days do you expect to sell between this and this amount? So the second one was the percent between, oh, no. Really? Let's go super quick here. Let's do it in hacker mode. You ready? Let's go hacker mode. Okay, we're going hacker mode. We're going super quick right here. You ready? Okay, we need to figure out the percentage between, and we'll see what people said for the questions. Here's the question right here. Let's go quick mode on it, because we're going to do more questions after this. Well, hacker mode is on. It's hacker mode if you haven't seen it. Okay, so we have right here, what percent is between 170 and 260? With our curve, we have a big help. So 170 is down here, and 260 is up here. Now, the first thing I'm going to do is I'm going to divide this into parts, and I have region 1, and I have region 2. Now, region 1 is going to be half of the 68. If you look right there, region 1 is half of the 68 because this is all of 68. So that's half of 68 right there. So that makes region 1 right here worth 34%. 34% right there. Then we're going to go over here to region 2. Region 2, you're going to see a double overlap right here, is half of the 95. See, here's 95. This is all 95 covered. And then we're taking half of 95. So 95 divided by 2 is 47.5. And then we want the total of these areas. So for the total of these areas, we're going to take 34 plus 47.5. And there's the answer right there. We got some Chapter 8 votes. Chapter 8. Can we expect a question that asks what the 80th percentile between z-scores? We wouldn't do the 80th percentile. So we wouldn't do the 80th percentile right here. We would do something. We'll take off hacker mode. The numbers you're supposed to memorize. What are the numbers for the empirical rule that you must memorize? What are the numbers for the empirical rules that you must memorize? What are the numbers for the empirical rule that you must memorize? What are the numbers for the empirical rule that you must memorize? And a theoretical question could be, I'll ask in a second right here, and then we might do chapter 8. That's the only vote I see so far. And I like that O right there. I was just like, oh, I get it. Oh, I get it. 68, 95, 99.7, 68, 95, 99.7. But what if a question were to ask, theoretical question, What would the z-score be? Like, let's say, here's a question. You ready? What is the z-score of the 80th percentile? So here's the possible answers. A will be negative. Actually, I should know something close to this. Oh, I do know it. I do know. Wait, no. Give me 2 seconds. No, let's go right here. Go to 90th. No, I don't know the 80th off the top of my head, so I know the 90th. Okay, so I can put in a real answer for this. Okay, so what is the z-score for the 90th percentile? Okay, I got it. Negative 1.2816. B is going to be negative 0.673. I think that's good enough, yeah. And then C is going to be 0.673, and D is this right here, 1.2816. Okay, what is the z-score for the 90th percentile? Who knows the answer to this? This is something. I just clicked a button. Okay, good, we're good. What is the z-score? And yeah, Cody, great job right there. Cody, great answer. Cody is correct, and everyone. So the first thing you should note is it has to be positive, because instantaneously we know that the 90th percentile is above the 50th, and the 50th is right here. That's not 56. Brian, your handwriting. You need to improve this. This is the 50th percentile, but then people might also say, well, then how would you know? Like, how do you pick between C and D? We've narrowed it down to C and D. How have you decided which one it is between C and D? Everyone's saying D, and you are correct. Exactly, Jensen. Amazing work, Jensen. I'm just going to put random dots on the screen. Jensen is 100% right that at this, we would have the 84th percentile, and over here, you would have the 97.5th percentile. And this is where I'll show the normal curve again. So the answer to the question is going to be right here is where the 90th percentile is going to be, which is not something we memorize. And so, and Ella, great job right there. That's exactly it. And you can see it by all the numbers we can get from the empirical rule. So I need to pull it back up again. I guess I closed it down. 2 seconds. I've downloaded this about 50 times now. And you can see it right here on the curve that this is where the So yeah, here's the 84th percentile. It might be I hope it's not too hard to understand. This is a mega drawing, but the 84th percentile would be right here. So there's a lot going on this screen, and I think chapter 8 is what we might do next. What votes do we have? Let's take a vote. I think we got chapter 8, pivot. So here, let's go 8 as vote 1 or vote 0. Give me a moment here. Let's just reset the vote and let's vote again. Okay, so here's the vote again. So time for you to vote. Probably be the last topic we'll do today. We'll be doing more review, and we'll try to do new things every day when we get time to review. But go ahead and vote right now. 0 is pivot, and every chapter is the associated number it is. So this is your chance to vote right now. We'll give it a moment. This is your chance to vote. Whoever has it's a close vote, so you can get your votes in. I don't know what to do if it's a tie. Let's see right here. We'll put a 1-minute timer on, and I'll come back. Oh, that's 30 seconds. That's better. Okay, 30-second timer. At the end of 30 seconds, we will go with the vote. I'm just going to pause on this screen right here so you can see right here the curve. These are all the numbers that you can get via the empirical rule. You have 68, 95, 99.7. These are the percentiles going up, as in this is the 97.5th percentile. This is the top 2.5 because 100%. This is the top 16%. And there's not, oh, it is the top 50%. Look at that. Here's the mean. It is written with that. Oh, time to check the vote, if you heard that. And let's see, Mubot, stop the vote, stop the vote. Yes, stop the vote. No, come on. Okay, first vote to come in. We're revoting. First vote to come in. You can watch it live here. First vote to come in, we're going with. First vote to come in, we're going with. First vote to come in, we're going with. First vote to come in. I'm going to watch the screen. First vote to come in, we're going with. Boom, right there. We're going chapter 8. Saw it. So that means you were watching live. It was look at. Oh my God, I love it. Oh my God, it's so crazy. I'm losing my mind, everyone. Okay, that's awesome. Okay, we're going chapter 8 because it's first vote to come in. Just tiebreaker, just like flipping a coin. Could have went randomness. Could have went randomness. Everyone knows we love some randomness in this class. So with that, and remember, we will be reviewing more, especially during class. I'm going to try to do new stuff every day for these videos. Let's talk about some Chapter 8. Chapter 8 is all about what, everybody? Chapter 8 is all about what? I'll put this here for myself. Chapter 8 is all about what? Can something be practically significant and... Yep. Once we have statistical significance, it opens the door to practical significance. It needs to first be statistically significant, and then we can examine the idea of it being practically significant. So first you talk about statistical significance, and then that opens the door to practical significance. So... Okay, cool. I'm good on, okay. It's all about linear regression. So this is linear regression topics. And let's do, it's called Regression Wisdom. Regression Wisdom. Let's talk some Chapter 8. It's a shorter chapter, and let's do this right here. So when it comes to Chapter 8, probably one of the biggest topics to talk about is going outside the bounds of the model. So when we go outside the bounds of the model, let's talk about this concept right here. You're going to have people who study 0 hours for the test and people who study up to, say, let's say 10 hours. And you've got this relationship right here with a what sort of thing. What is the strength, direction, form of this? Who can talk about the strength, direction, and form of this? What is the strength, direction, form, and unusual features? Sure, why not? Strength, direction, form, and unusual features is the way we describe a scatter plot. So we have a scatter plot, Chapter 6 review right now. Strength, direction, form, and unusual features. What is the way we describe this? It's definitely positive and strong, so it goes up. That means it's positive. It's pretty strong right here by the tightness of it, which means it's closer to 1. What is form? Form is either linear or form is not linear. So either something is linear or not linear. So form is like, is it a line or is it not a line? And not a line can be a lot of things. Like not a line can be anything that's not a line. So no, great question, Jensen. Always great questions right here. So we have here strength, direction, form, unusual features. The strength is it's pretty strong. The direction is that it's positive, it goes up. The form is that it's linear, it follows a straight line. And the unusual features is that there is an outlier right here. Strength, direction, form, unusual features reviewed. So sure, outlier's gone now. Now it's a great regression. It's exactly. And so when we think about this, your friend says, you know what? They said, I've been failing Stat 201. I decided I don't need review sessions. I don't do my Canvas content. You're like, what do you, come on, man. It's how you talk to your friend. They say, I don't need to do the Canvas content quizzes. I don't need to do the visualizations. I don't need to do anything. What I'm going to do is I'm going to study 100 hours. So this is how long you study. They say, I'm going to study 100 hours. And my grade on the final, let's see, we have 45 points there. So that'd be like another 400 points. So they say, I am predicted to make, according to this model, according to the model Brian showed us, I would make like a 495. And so they're saying they're going to make a 495 according to this model when they study 100 hours. So for 100 hours of study, now this should be pretty clear. What are they doing? What are they doing with this model here when they go beyond the x-axis? Oh, I can't remember the word. Think of the x-axis, and you are whatting? Extrapolating. Just always start with the x. And to think about like extrapolate from something means to go outside of it. So this is an extrapolation of the model. So we have this example right here. So you say, look, you're extrapolating from the model. One, that's not even possible. They don't give out 495s in this class. And they're like, what? And you're like, yeah, you need to go to class. You need to do your Canvas quizzes if you want to pass. So you'd say you're extrapolating right here. Ben's like, dang it, Brian, you ruined my plans. No, I'm just kidding, Ben. So with this right here would be extrapolating, and you'd be going outside the bounds of the model. I think, Ben, you know what's going on. Ben, you're awesome. So let's take a look right here. And what about this model, though? This model, Taco Bell with their taco fries. Taco fries? Oh, my God. Taco fries. Oh, that's They could do. What's the tier? Did someone get a new tier? Did you just get there, Ben? Ben's like, what'd you get, Ben? I want to see Ben's tier as we talk about this. Taco Bell is talking about. Nice job, Ben. Ben is at. Oh my gosh, hero returning. Nice job right there, Ben. So awesome. I'm so proud of everybody with all the points. Taco Bell has between 80 customers and 400 customers a day. And so this is customers. How am I able to do a scatter plot with this? Why am I able to do a scatter plot? Wait, you can go above. Kyle, expand upon that, and I'll explain. I'm trying to understand about above 2 points. Oh, you can. Oh, you're talking about that. Yeah. The higher and higher levels are very small amounts. Oh, you got it. Hey, it's all in good fun. The points you get, like, I mean, they do count, but so this is nacho fries. Put your fries. Nacho fries. So this is units of nacho fries sold, all the way from 40 units of nacho fries to 300 units of nacho fries. I do not need to be eating nacho fries. So there is a positive linear, strong relationship between number of customers who go to Taco Bell and the nacho fries they sell. I don't know who's the highest right now. Calzone and Andrew have some pretty interesting points if they ever show their points. Maybe we'll show them off during the thing. They're not in class anymore, so they get kind of interesting statuses. So with this right here, and great job, everybody. What do you notice about this? This is Andrew's showing his points though. What is the tier? Oh, you're about to see in a moment. So with this right here, here's the question, when would they be extrapolating? When are they extrapolating with this model? Think what extrapolation means. So think about extrapolation. Think about extrapolation. When are they extrapolating on this model? Be very careful. You are right, Jensen, and then Ella points out the other thing. So this is beyond the bounds of the x-axis. So an important thing, a lot of people think it's just over 400, and Emily and everyone else catches a great job, because this is the trick I like point out. It's anytime you are outside the bounds of the x on the model. So we'll do it in red, not green. I want to use red. We'll do it in red right here, because it's generally a bad idea to take the model and go beyond where the x data is. So in these instances, you are extrapolating outside the model. Don't worry, this is like I said, I always keep saying this is the practice. This is the practice right here. So you are extrapolating beyond the bounds of the model when you leave the x's that were used to create the model. And sure, it goes to 400. Wait, let's take that. Oh no. I meant to have the data go to 400. So we're just going to pretend that data goes right to 400. And whoa, look at that. It's perfect now. Hey, it's good practice. It's just, you got it, Jensen. You got it down. You're answering. Boom. And you know that now that an extrapolation of a model is when it goes outside the x bounds of the data. So you can have instances where only kind of positive extrapolation would be possible. So in this instance, you really can't study negative hours. So you can't extrapolate on the low side of this model. You can only have here extrapolation on the high side. And then for this example right here, you could extrapolate. And once again, why are we able to do regression? You're welcome, Cody. Excellent work. We're gonna head off here in 9 minutes and do stay to the end. It'll get pretty interesting at the end. So we're gonna end at 6:50, and then we are doing a Kahoot at the end. So do stay till the end. We got a special guest appearing, super special guest. So stay to the end. Why can we do a scatter plot right here? Why can we do a regression with a scatter plot? Like, a very important thing about these right here. Why can we do a regression with a scatter plot? Why is it even possible to do a regression with a scatter plot? Why is it even possible to do regression with a scatter plot? QQ, exactly. 2 quantitative variables. Exactly. Great job, everyone, right there. And to review, we've kind of talked about chapter 8 is a pretty big review chapter. 2 quantitative variables. Exactly. QQ, straight enough. No outliers. I swear I literally had someone yell that to me when I was on the strip. Probably getting some Taco Bell. I thought about Taco Bell and I lost it. I was like, Taco Bell. Okay, let's do a quick review of the 4th condition again, because that is in chapter 8. QQ straight enough, no outliers, plot doesn't thicken. We went over all the conditions at the start. What we want to see for plot thickening is we want to see a what thickness throughout the plot for the points generally speaking. We want to see a what thickness throughout the plots for the points generally speaking. And this one's all right. I'm not going to make it perfect today. That one's okay. That's okay. I know that's a little thicker, but what do we want to see when we want plot does not thicken? What do we want generally speaking? This one's okay. Uniform thickness throughout, like same thickness throughout. Usually we want to use these things. I know, Ben. I still like it though. Taco Bell's Taco Bell. Now, here's where people make a mistake a lot of times. Well, let's look at this model right here. This model is getting weaker or stronger as you go to higher values of x. As you go to higher and higher values of x, this model is getting wetter. The first model, model number 1, we'll give it a number right there. Model 1 it's getting weaker. Exactly, it's getting weaker. The predicted power of the model is getting worse. Now, what do we do to make a residual plot? We haven't talked about this today, so really good talk on this. How would we turn this into a residual plot? How would we take this right here and turn it into a residual plot? How can we take that and turn it into a residual plot? How do we make that a residual plot? So what do we do right here to turn this into a residual plot? So you take it, turn it into a residual plot, you take the plot, make the screen go crazy. So we need to shrink it down a little bit. Take it, make the line straight, exactly. And then what do we do? So we make the line straight, and then we go over here, grab the white pen. We're just kind of drawing a new plot on it, and the line will be set to what? So this is how a residual plot is. We're making a perfect residual plot here. We make the line straight, and then the line is set to what? The line is set to 0. Exactly. Great job right there, Parker. Excellent work. The line is going to be set to 0 right here. So now we can see right here the residual, like this point up here has a very positive residual, and that is that same point. We literally graphically altered this to make it a residual plot. Does this make sense how a residual plot is going to show you all the residuals? And once again, what do all those residuals add up? If I take all the positive residuals and all the negative residuals, what do they add up to? These are big things you should know. If you take all the positive and the negative residuals, because these are the negative residuals now, they're in the same spots as the previous graphic. They all add up to 0. We should know that instantaneously because the line does that. The line of best fit creates this sort of relationship where we have positive and negative residuals kind of balancing out the line. And the same thing works here. These are the positive residuals here, and these are the negative residuals. Now, the first graphic is showing a heteroscedastic. I shouldn't say that word. Stop saying it, Brian. It's showing a plot thickening relationship. There is issues here of plot thickening, which can also be seen in the residual plot. The residual plot is the same graphic, just the line is made flat. The second one, this is where people usually get confused. It looks good. And if you were to take this and turn it into a residual plot, let's see what happens. This is where people get super confused on this. They say, wait, this doesn't look good, but it totally does. This graphic right here, when you make it flat, it's going to look pretty random. And that's actually how a good residual plot looks. A good residual plot is going to look completely and utterly by... It is a little bit like, yeah, it's like kind of like you're playing games with the image a little bit. And this is a good residual plot now. It's just the line flat. This is the first graphic, or the second graphic, excuse me. So we're taking this and we're just going to make the line flat because the line is set to 0 because everything on the line, my horribly drawn line, for the Canvas Contour Quiz 4, could I use my second attempt for just extra practice? Yeah, I think you can. Yeah, Tori, you can. It shouldn't lower your grade. As long as you got 100 or, yep, I would definitely use your second attempt. Great job right there, Tori. Excellent work. So if you notice here, everything on the line would have a residual of 0. And with that, don't leave yet. And remember, let's drop the link in for the Kahoot. Tell your friends to join the Kahoot. The more people we have playing the Kahoot, the more fun, the more just like Hoot it is. The more Kahoot is. I don't know. Give me a second here. I'm going to pull up the Kahoot link. I'm going to drop in the chat. We got 55 people watching. That is awesome. Come here for any of the reviews you want. We got the knowledge test, 13 minutes. We're going to drop it in here. Okay, there it is. I think I have the link. Here we go, Kahoot. Let's Kahoot spam the chat real quick. There is the Kahoot link in the chat. And just give me a second right here, everybody. I'm going to fly back to Knoxville really quick. I'm going to go to my office. So give me a moment here, everybody. I'll be right back. Just going to go to my office really quick right here. One moment.
Hey Brian, what's up?
Hey, Adam.
Oh, what's this?
Adam, what are you doing? Adam. No!
Guys, I'm Jason. Brian's gone. I don't know. I don't know. Just go to Kahoot. We'll get this figured out. He sent you the information. It's on Canvas. It's on YouTube. Just go to Kahoot. I don't know what we're gonna do, but we're gonna figure this out. It's gonna happen. That's all I got. Just go to Kahoot. Thanks. Ugh.
I am Mubot.